Hello and welcome to our discussion on acids and bases, properties and nomenclature. In the first video for this unit, we're going to focus in on just what acids and bases are um, and reinforce what you might already know and just kind of lay the landscape for what's going to happen the next few weeks. Keep in mind from our solutions understanding that when we see brackets, it means molarity, it means concentration. So if we see the symbology there, hydrogen ion concentration equals 1 molar, that's what this means. Don't get thrown off by seeing brackets. So an acid produces hydrogen ions when we dissolve it in water. Okay. Most acids we're ever going to encounter are already dissolved in water, but you'll find a few. Um, at the grocery store, you can find citric acid for canning. Um, that's just what you would think it is. You taste it, put it in your mouth, it's sour. Um, uh, Vinegar contains acetic acid, about 5 or 6%, I think. Lemon juice, citric acid, like I just mentioned. Sour candy has malic acid and many other different acids. Um, make things like Sour Patch Kids taste the way they do. And then milk contains an acid called lactic acid. And we'll discuss a whole bunch of other acids in the next uh, few discussions and lectures. So um, just some big picture stuff about acids. So, it's not all what you see in movies where there's this thread of acids eating through the floor and things of that nature. It's uh, not very steeped in reality. They have lots of very practical applications. Most of them are consumable. Um, and then, of course, there's the ones we use in chemistry. Um, like I mentioned a moment ago, acids taste sour. If you put a bit of acid in your mouth, it's got a very sour taste. When you expose most metals to acid, they're going to react and produce hydrogen gas. And if you recall, uh, your hydrogen um, your hydrogen location on your activity series for metal, you probably remember that it's going to react with most metals. There's a few that, in theory, in absence of other reactions, you won't see um, acids react with metals, but uh, this is generally speaking what you're going to see. There's this reaction here. This is magnesium and hydrochloric acid. Let me go back and reset this. Zinc and hydrochloric acid. If you put them together, you don't get much of a pow. You get more bubbles. We saw this similar with magnesium in our molar volume of a gas lab. If you recall, we produce hydrogen gas. It would be no different if we place zinc in the container when we produce zinc chloride. Um, I wouldn't call it a violent reaction, but it is exothermic. Let's go back and look at a couple other properties. Acids turn blue litmus paper red. So if you take a piece of blue litmus paper, there's two types. There's blue and red. Blue litmus paper in the presence of an acid turns red. Another important distinction is aqueous solutions of acids are electrolytes. That's because most acids dissociate enough in water to form enough ions to conduct an electric current. Acids, when you put them in presence of a base, will react completely. Whatever one may be limiting is going to react completely with the other, and the products will be salt and water. If they're equimolar, then all that's left when you put an acid and a base together is whatever salt their cation from the base and anion from the acid create, and new molecular water. So this is that same reaction. If we take acetic acid and sodium hydroxide, it doesn't matter if it's strong or weak, you put them together, you're going to get a new salt and water. And we talked about net ionic equations last unit, and so we would know that if this ionizes completely in water and this ionizes completely in water, then sodium would be a spectator. Whereas acetic acid, we'll find later, is not a strong acid, so it doesn't get removed, but that's a different topic. Sulfuric acid, barium hydroxide, same thing. We'll get barium sulfate as a product and water as a product. And then, of course, two strong acids, hydrochloric and sodium hydroxide, making sodium chloride and water. So theoretically, equimolar solutions of very dangerous corrosive acid, very dangerous corrosive base, equimolar, reacted together, forming only salt water. Perfectly safe. Go back to our properties. So speeding forward into naming, into what we've been looking at, we're going to move into nomenclature for acids. Now we've done this before, and so I'll go relatively quickly. Just remind you of a few key ideas. Um, binary acids begin with hydrogen, are hydrogen bound to one nonmetal. For example, hydrofluoric acid. We use the prefix hydro. Okay, so hydro, and then the root for whatever the anion would be. In this case, fluor, or in this case, bromic, hydrobromic acid. Ternary acids are also known as oxoacids or oxyacids, are hydrogen bound to a polyatomic ion that contains oxygen. They begin with the polyatomic ion, but without its suffix. And so if you had, for example, nitric acid, pardon me, HNO3, nitrate is your anion, you would remove the suffix ate. And since it was ate, you would change that suffix to it, nitric acid. So if the suffix was IC, you change it to ate. Sorry, if it was ate, you would change to IC. If it was ite, you would change to OUS. So this would be chlorite. Chlorite would be chlorous acid. Keep in mind the reason these are called oxyacids, oxoacids, is because oxygen is part of that polyatomic ion. This is a little nomenclature issue we've always had, but just to make it clear, when you have acids of sulfur and phosphorus, we use the whole root for the whole, or a larger root than you would think for the stem. You say sulfur instead of sulf, or phosphor instead of phosp. Not not phos. So it's sulfuric acid, not sulfic acid. Phosphoric acid, not phosphic acid. Um, real briefly, organic acids are very important too. We won't feature them much because they're not really a topic for this course, but the question comes up a lot, so it's best that we kind of just look at it a little bit. Um, organic acid, or better known as carboxylic acids, they contain a carboxyl group, which is oxygen doubly bound to a carbon with an additional hydroxyl OH group bound to that carbon as well. And so in any carboxylic acid of any length, you're going to have this group that's highlighted here and here. Okay, this is formic acid. This is the active ingredient in ant bite venom. This is acetic acid, the active ingredient in vinegar. Just very subtle difference, one carbon length difference. And then here's a nice laundry list of many different acids that are common, from butyric acid, which is common in butter. It's also the acid that makes vomit smell terrible, or one of them. And then kind of a nice little list of some common carbon length carboxylic acids, and then some images too. Benzoic acid here is one of them, butyric acid here, just with that carboxyl group at the end. Acid strength is key. We have to understand what constitutes a strong acid versus a weak acid. But what does it mean? Strong acids ionize completely in water. And in this diagram, what we see, we have hydrochloric acid mixed with water. What ends up happening when you place hydrochloric acid in water? Because it's a strong acid, the hydrogen and the chloride split. The hydrogen ions bind onto water, and the chloride float free in the solution completely. It ionizes completely, where weak acids do not ionize completely. In this example, we have sulfurous acid, which is a weak acid with water forming hydronium and sulfite ion only rarely. In a true solution of sulfurous acid, we would have less than 1% of all of our acid actually form ions. There are three strong binary acids: hydrochloric, hydrobromic, hydroiodic. These are the only three strong acids that are binary there are. Hydrofluoric is not a strong acid. And the reason is that fluorine has a significant attraction to its hydrogen, so significant that water molecules can't split that bond. And since they cannot, hydrofluoric acid in water stays molecular, stays the molecule. HF does not get ripped apart. There are four strong ternary acids, though one is up for debate. But for our purposes of our course, we'll talk about these four being considered strong. First is sulfuric, nitric, chloric, and then perchloric. The one that's fuzzily strong is chloric acid. We can get into more details in AP chemistry about why that is. But these are the only four strong ternary acids we'll talk about. So you have 7 total strong acids. You need to know them. You need to memorize these. It's a fundamental fact in all of chemistry. We need to know which acids we expect to ionize completely in water. These are they. Know them. Bases. This will go a little quicker because you're kind of familiar with what we did. The acids. So bases typically in water will produce hydroxide ion. This is a general theory. We'll get more into theory in the next video. Some common bases that you might know of: milk of magnesia. It's used to treat um, dyspepsia, it's the irritation of the stomach. Drain cleaner, sodium hydroxide, is used to clear drains, obviously. And ammonia, that's in window cleaner. Um, really, this isn't ammonia that's in the solution. When you put ammonia in water, it makes ammonium and hydroxide. Um, so you don't really get ammonia in water. Ammonia is a gas. Um, some common facts about bases: typically they taste bitter, though few of them, you're not going to have a recognizable taste from any of them. They feel slippery to the touch. If you ever get bleach, chlorine bleach on your hand, you'll notice that slipperiness. That's the desquamation of your hand taking place. If you get it on your fingers, it's literally just sloughs all the dead skin cells off your fingers, off the outer layer of your skin. Not that it's hurting you, but it can chew through enough of that dead skin to get down to your bare skin and become painful. That's why bases are just as dangerous as acids in some ways. Um, bases will turn red litmus paper blue, the exact opposite of what happens with acids in the presence of blue litmus paper. Aqueous solutions of bases are also electrolytes, and just like acids, of course, they react with acid to form water and salt. The nomenclature for bases is the same as it is for any ionic compound except for ammonia, which you need to know, but most of you know it by now. We use the rules we would use for anything with polyatomic ions. We name the cation, we name the anion. Um, this is a typical ionic naming: sodium hydroxide, calcium hydroxide, potassium hydroxide, magnesium hydroxide. Nothing really difficult to see here. Base strength: strong bases completely ionize in water, just like strong acids. Hydroxides, sorry, bases of group 1 and 2 metals, with the exception of beryllium, are considered strong. Now, the problem with this is that not all these are soluble in water. Go back to your solubility rules, you'll remember that. Um, lithium hydroxide, sodium hydroxide, potassium hydroxide are pretty much soluble, but rubidium and cesium not so much. And if you get into the hydroxides here, there's not great solubility among the group 2 hydroxides. The trick is, if you can get them to dissolve, they ionize completely. So they're considered strong bases. So for the purposes of this unit, you don't need to worry about the degree to which they're soluble as much as knowing which ones are considered strong. Weak bases ionize only slightly. Anything else that's not listed there, like ammonia, for example, is a weak base. Aluminum hydroxide, weak base. Copper 2 hydroxide would be a weak base. Anything that doesn't contain a cation from group 1 or group 2 would be considered weak, exception beryllium. And that is it for video number 1 for bases and acids. Please make sure you've taken high quality notes. If you have to rewind, go back, make sure you've got everything you need complete. Check out falconchem.com for our resources attached to this video and unit, and we'll see you in class.